Lesson 3-4, transformations of linear functions. You can see here on the slide here, we have different functions, but they were just transformed a little bit by tweaking it, and that's just changing either the y-intercept or changing the slope of the line. So that's what we're going to look at today. So some translations. We have everything's all based on this parent function. The parent function is f of x equaling x or y equals x. So for linear functions, everything is based off of that. Now the transform function would be f of x or y equals a times x minus h plus k, where h and k is your translation. So this would be the set standard for transformation. We're going to look at each one today. And then we'll look at dilations, which will be referring to the letter A. So if K is a positive number, means it's bigger than 0, and K is right here, which is in our place of our B, that means the whole graph of y equals x gets pushed up that many spots. So if it was g of x equaling x plus 4, I would have to move the whole line up 4. So if we're starting at 0, 0, if I move it up 4, that's where the whole line would be. Everything else should stay the same. The lines would actually still be parallel because your slope never changed. Now if k is negative, and say we had a minus 4, that means we would start at 0, but we would go down to negative 4 here. So the k is always telling you, are you translating it up or are you translating it down? And whatever number they give you, that's how we move it up or down. Now the h is referring to your x. It means you are working on your x-axis, and you're moving it from right to left or left to right. So if h is positive, and this can be the tricky part, because inside the standard form here, you have x minus h. Right now, h is positive. So when h is positive, it goes to the right. And then when h is negative, and you'll know that h is negative because it'll look like this. You have x equaling x plus h. And why is that negative? Because if I were to rewrite it this way, minus a negative h, this is the same thing as saying x plus h. So for me, when I'm doing this, I always know that the parent function, x is at 0. So if I take x minus h and I set that equal to 0 and I solve for x, that's going to tell me where I need to have my line crossing the x-axis, or which direction I need to move it. So if I were to add x to both sides, here I would have x equaling a positive h, which just means I'm going to the right. Here's just in a table format. When you have a positive k, you go k units up. When you have k is negative, you'd want to go down. When h is positive, you go to the right, and when h is negative, you go to the left. Now let's take a look at some examples. Let's describe the translation in each of the functions as it relates to the graph of the parent function. And the parent function would be g of x equaling x. So right now we have g of x equaling x minus 2. Since the k is a minus 2, we are going down 2. This next one, here because this is in parentheses, that 5 is attached with that x. Because really there's a plus 0 at the end. We just don't put the plus 0 there. So it's not going up or down. This is actually going right or left. So this is what I would like to do. I would take this x plus 5, make it equal to 0, and then solve for x. If I were to subtract 5 on both sides, I would have x equaling negative 5. So if x is at 0, where is it? Where is negative 5? Negative 5 is to the left. So this would be shifted left 5 units. Next, describe the translation in g of x equaling x plus 12 and it relates to the graph of the parent function. Again, the parent function would be g of x equaling x. Since this is in parentheses, I know it's moving right or left. I'm going to set that equal to 0 and solve. So I'm going to subtract 12. I would have x equaling negative 12. Negative 12 is to the left of 0, so I would go left 12. More examples. Doing the same thing here, it's plus 3, which means no parentheses, it's going up 3 units. This one, the 7 is in parentheses. I do x minus 7 equaling 0. I add 7 to both sides, and now I would have x equaling 7, which means it goes 7 to the right. In example 2, describe the translation in g of x equaling 6 plus 3 as it relates to the graph of the parent function. And our parent function is g of x equaling x. We have two translations, right and left, and then up and down. So first off, this plus 3 here, this plus 3 tells us it's going up 3. And here, this one, I would have x minus 6 equaling 0. Add 6 to both sides. X would equal positive 6. Positive 6 is to the right of 0, so this would go right 6. So our translation would be up 3 to the right 6. Next, we have x plus 4 in parentheses minus 10. So I know it's going down 10. And here, because I know this is if I rewrite this in standard form, it'd be x minus a negative 4. My h is negative 4. So I know that's left 4. Or again, you could do x plus 4 equals 0, subtract 4, and I would have x equaling negative 4, which means that's to the left of 0. So our translations would be down 10, left 4. Here we got a work problem. The website sells tickets to concerts and sporting events. The total price of the tickets to a concert game can be modified by f of t equaling 12t, where t represents the number of tickets purchased. Website then charges a standard service fee of $4 per order. The total price of an order can be modeled by g of t equaling 12t plus 4. Describe the translation of g of t as it relates to f of t. So f of t is just 12t. G of t is 12t plus 4. So what is the difference? The only difference is this plus 4. So what does that mean? The translation, it went up 4. Next question, Drew is buying paint for a mural. The total cost of the paint can be modeled by the function f of t equaling 6.99p. He has a coupon for $5.95 off his purchase at the art supply store. So the final cost of his purchase can be modeled by g of p equaling 6.99p minus 5.95. Describe the translation in g of p as it relates to f of p. Now the difference is this minus 5.95. So that means this went down 5.95, which just means it's just $5.95 cheaper. Next, for a school field trip, students are going to a museum. The total number of people attending can be modeled by the function f of b plus 48b, where b is the number of buses of people. 20 additional people are coming by car. The total number of people on the field trip can be modeled by g of b equaling 48b plus 20. Describe the translation in g of b as it relates to f of b. Here's our f of b, here's our g of b. The only difference is this plus 20, so it is up 20. And that would just be 20 more people coming by car. Moving on to the next part of our lesson, which is on dilation. Dilation just refers to the stretching or the compressing of the graph of a function. When a linear function of x is multiplied by a positive constant a, the result is a times f of x, and it's a vertical dilation. So a stretch means you're going in both directions, up and down. A compression means a vertical compression means you're squeezing it from top to bottom, so you're making it flatter. So when it comes to our graph, it says if the absolute value of a is greater than 1, then the graph is a stretch vertical. So if you take the blue line here and you're multiplying it by a number greater than 1, it's now steeper. The gold one is steeper than that, so it's a vertical stretch. You're just taking the arrowheads and they're stretching it upward, or they're stretching this one downward. So the slope of the graph of a times f of x is steeper than that of the graph of x. Now, if the absolute value of a is between 0 and 1, less than 1, then it's compression vertically. Just means I'm taking the blue line and I'm pressing it down in both directions, and it flattens it out. So it's less steep. When x is multiplied by a positive constant a before a linear function of x is evaluated, the result times a times x is the horizontal dilation. So you notice the difference here is that a is on the inside of the parentheses, so it's affecting the x, which means it's a horizontal dilation. And just like vertical dilations, horizontal dilations do have compression, but they're just going to be the opposite. So if the absolute value of a is greater than 1, you're going to be compressing it horizontally. It just means you're squeezing the blue in from the sides. And when you do that, it makes it longer, the gold one longer. So compressed horizontally is the same as a stretch vertically. So the slope of the graph of a times x is also steeper than that of the graph. So here, this one really should be f times a times x. And this one also should be f times a times x, because this is a horizontal dilation. Here, for a stretch horizontally, that means I'm stretching it horizontally. I'm going outward like that, which just makes it flatter. So a stretch horizontally is the same as a compression vertically. Example 4, describe the dilation in each function as it relates to the graph of the parent function. Again, the parent function would be g of x equaling x. So this 2 is on the outside, and because the 2 is on the outside, this is a dilation, but this would be a vertical dilation. And the absolute value of 2 is bigger than 1, so this is a vertical stretch. And if we want to be a little more specific, we can say that it's a vertical stretch by a factor of 2. Next, g of x equaling 1/4 x. You notice the 1/4 is in parentheses, so this is also in front of the x. So this is a dilation, but because it's on the inside, this is a horizontal dilation. And now I have to look at the absolute value of 1/4 is 1/4. 1/4 is less than 1. 1/4 for a horizontal would be a horizontal stretch by a factor of 1/4. Now, one way for me to think of this is I'm going 1/4. So if I think I'm going up 1/4, in order to do a horizontal movement, I'm going out in both directions. So this is a stretch in both directions. So it's going long horizontally, which would be a stretch on that one. Next, describe transformation g of x equaling 6 times parentheses x as it relates to the graph of the parent function. 6 is on the outside, that's our a. So we have a dilation. If it's on the outside, that means it's a vertical dilation. And the absolute value of 6 is greater than 1, so this is a stretch by factor of 6. Now, if the 6 was on the inside of the parentheses, then this would be a horizontal compression. Actually, no, yeah, a horizontal compression if it was on the inside. Next, describe these transformations. So 0.65 is on the outside, so this is vertical. And vertical translations, or vertical dilations, can be a stretch or a compression. Since 0.65 is less than 1, and it's a vertical, so this would be a vertical compression. And this wouldn't be as steep. Next one, the 8 is on the inside, so this is horizontal. And the absolute value of 8 is 8, which is bigger than 1, so this is a horizontal compression. That means it's going up 8, going over 1. In order to do that for a horizontal movement, you have to compress it inside to make it longer or more steeper. Moving on to the next part, reflections. Reflections is referring to positive and negative. So if there's a negative in front of the A, you have a reflection. And where does it reflect? In the left-hand box over here, we say the graph of negative f of x is a reflection of the graph of f of x across the x-axis. So it's actually affecting your y in the end. So if the negative is on the outside, it's going to affect your y. So you have a positive y going to a negative y. So it's a reflection over the x-axis. And the graph of f of negative x, so if the negative is on the inside of the parentheses, it's affecting the x. That means it's crossing the y-axis, going from a positive x to now a negative x, or a negative x to now a positive x. So example 5, describe how the graph of each function is related to the graph of the parent function. So the first thing we need to do is, well, we notice that there's a negative, so there is a reflection. It's on the outside, so it's affecting the y. So if it affects the y, it's reflected across the x-axis. And then the half is on the outside, so this is a vertical translation, or vertical dilation. And the absolute value of negative half is positive half, which is less than 1. So this would be a vertical compression. Letter B, g of x equaling negative 3x. Negative 3 is on the inside, so this would be a horizontal dilation. And the absolute value of negative 3 is 3, which is greater than 1. So this would be a horizontal compression to make the slope steeper. And then there is a negative, so it is reflected. And it's on the inside, so it's affecting the x. So it's reflected over the y-axis. Next, reflection across the x-axis. Letter A, if the constant is not grouped with x, the result would be a reflection across the x-axis. B, if grouped with x, the result would be a reflection across the x-axis. C, if the constant is greater than 0, the result would be a reflection across the x-axis. Or D, if the constant is less than 0, the result would be a reflection across the x-axis. Now the constant has nothing to do with the reflection part. So that one has, that's not going to do anything with that. It's all depending if it's grouped with the x or not. So if it's reflected across the x-axis, that means it's on the outside of the parentheses. So it's affecting the y. So that means it's not grouped with the x. So that would be letter A. Next, describe how the graph of each of these functions is related to the graph of the parent function. Again, I have a 5 sided dilation. It's on the outside, so this is vertical. Absolute value of -5 is 5, which is bigger than 1, so this is a vertical stretch. There's a negative involved, so it's reflected over. It's not attached to the x, so it's affecting the y, so it's reflected over the x-axis. And letter B, the number is inside the parentheses, so it's a horizontal dilation. The absolute value of a -1/6 is 1/6, which is less than 1, so this would be a horizontal stretch. And there's a negative involved, so there's reflection. So this is reflected over. Since it's affecting the x, it's reflected over the y-axis. So that is our lesson on transformations of linear functions.